All right, so now you're not going to be showing yourself in there, right?
So I don't have to cut it out after.
All right, so we're starting with we're continuing with chapter 18, which is ethers and epoxide, thiols, and sulfides. Okay. By now, you guys have heard about solvents like diethyl ether, THF, tetrahydrofuran, and those solvents falls under the categories of compounds that are classified as ethers. We can consider those as organic derivatives of water. So if you think about it, H2O, and you replace those hydrogens with alkyl group, aryl group, or vinyl group, or allylic, right? So if you replace those H's with any of those groups, you get ether. Okay? But for thiols and sulfides can be considered as analog of alcohols. Okay, so if you look at alcohol, you have the alkyl group, and in this case, the oxygen that you have in alcohol has been substituted with sulfur. Okay, so they are sulfur analogs of alcohols. And to name them, it's very straightforward. Naming is very straightforward. This is one thing that you're sure will come in any quiz, any exam, naming of organic functional group. So, to name ethers, let's start with naming ethers. To name ethers, what you need to do is to identify the organic substituents that you have connected to the oxygen, and you add the word ether at the end. So for example, here we have an ethyl group because it's 2 carbon from ethane, right? You have another ethyl group here. Okay? So ideally you could say ethyl, watch this, ethyl ether, but because you have 2 ethyl groups, you use the word di, and that's how the diethyl ether comes into play. Diethyl ether. Okay, so that's how you get the diethyl ether. For the second structure we have here, over here is a methyl group. When you draw a skeletal structure of any compound, a line represents, the dot at the end of a line represents a CH3. Okay? So that's a CH3 at the end there, so it's a methyl. And over on this side is what group? It's an isopropyl group. Okay, so you can see how chapter 3 of Chem 251 comes into play. So you have to remember all those things. Okay, they are all connected. So now you have isopropyl versus methyl. I comes before M. So you arrange them in alphabetical order. So it's going to be isopropyl, methyl, methyl ether. Okay. On the next one, you have 2 isopropyl groups. There's one here. There's another there. So those are isopropyl groups. Therefore, it will be isopropyl ether. Okay, so that would be diisopropyl ether. Now, this is a benzene ring, but one of the hydrogen has been removed to connect that carbon to the oxygen. So it's no longer benzene, it is called phenyl. Okay? And over on this side is a methyl. So that's going to give you what? M comes before P. So it's going to be methyl, phenyl, ether. And what will be the last one? Should do that. What do you guys think?
Ethyl phenyl.
That's correct. So the last one is going to be ethyl phenyl ether. So you only use this naming rule if ether is the only functional group that you have in the structure. Okay? If that O with the alkyl group around it is the only functional group that you have. If you have any other functional group in the structure, okay, it's not going to be named as ether anymore. That is going to be like a substituent. Okay? It's going to be like a substituent. And what you're going to change the ether to will be alkoxy. Okay? That means an alkyl with oxygen. Okay, that's how you derive that, alkoxy. Okay? So here we have two of the ether functional groups, so it's no longer one, so we can't say ether. We cannot call this ether. Okay, we have to treat these as an alkoxy and that as an alkoxy. Okay? So if on your alkoxy you have one carbon, it becomes methoxy from methyl. If it is two carbons, it's ethoxy from ethane. If it is three carbons, it's propoxy from propane, and so on and so forth. If it is isobutyl on the oxygen, it becomes isobutoxy. Okay? So that's why you get the alkoxy in the name. Making sense? Okay. So, so for these, we have a methoxy on this side, and we have another methoxy here. So because there are two, it becomes what? Dimethoxy, right? But the parent chain now is these two carbons. Okay? And what is that two carbon? What is the name for those two carbon? Ethane. Huh? Did you say methane? Oh, ethane.
I said ethyl.
Yeah, but it's ethane,
Yeah.
right? Because it's the parent chain now, so it's ethane, right? So therefore, this is going to be 1, 2, dimethoxy, ethane. Why do we have to put that number? Because it's showing the position of the two methoxy group or the two alkoxy group. Okay. Another variation of this, we could have, we could actually have this. And what would the name of that be? Oops. What would the name of this be?
1,1 dimethoxy ethane.
That's correct. So this would be 1,1 dimethoxy ethane. Okay, so that's why the numbering becomes very important in that case. All right. Okay. So for the second example, I'm gonna separate this. You have a benzene ring Okay, you have a benzene ring. So the parent name there is benzene, but the methoxy are at position 1 and 4. So you can name this as 1, 4 hyphen dimethoxy. I'm going to write down here. Actually, let me go over there. Benzene.
To Delhi, could you use para?
Yeah, I'm going to go there.
Oh.
Yeah. Okay. So that is 1,4-dimethoxybenzene. Okay. But because it is di-substituted benzene ring, you can also use the conventional auto method para designation. Okay. So, but if it is more than 2, you cannot use that. Correct? Okay. So you could name this P dimethoxy benzene. Okay. Make sense? Good. All right, the last one there. So these can be considered, or is considered, your parent chain, correct? Because it has the double bond inside of the ring. And if you number this, it will be 1, 2, 3, 4. That is the closest distance that you can get to your alkoxy group. Because if you go 1, 2, 3, 4, 5, that will place the alkoxy group at position number 5. Okay? So this group is a cyclohexene group, and this whole group is what? Tert butoxy, because this is a tert butyl group. Okay, so you can say T butoxy, or you can write it in full as tert, T-E-R-T butoxy. Okay, and this tert butoxy group is at position number 4 off of the cyclohexene ring. Okay, so we can put 4 in front of it, right? To show that the butoxy is at position number 4. So if you want to put this in the name now, it's going to be 4 tert butoxy. I don't have enough room there. I'm going to start down here. Cyclohexene. Now, here's where students will say that, okay, it's too strict in grading. If you want to write cyclohexene and you write cyclohexane, if you change this to A, it's going to be incorrect. There's no way I can give partial credit for that because it's absolutely incorrect. It says something else. Okay? So you have to be careful with what you write. Yes?
Should you involve the number where the double bond is?
X1E.
Okay, so that's why the 4, so the 4 has given that away. Okay? Because it's at position 4 in relation to the double bond that you have in the ring. Okay? Make sense?
So what's the main difference again between when you would use ether and when you would use alkoxy?
Okay, so the main difference is if you have any other functional group other than the ether. So if you look at this example, for example, you have the ether there, and then you have the double bond in the ring. So that's 2 functional groups. If you look at these, you have the benzene as a group, and then you have the ether. Okay? And if you look at this, you have an alkene with 2 ether groups. Okay? So that's the difference. If it's only 1 ether group, then you go as ether. Okay? Make sense? Very good. Alright, so that's about naming. Okay? So you should practice more of that. Now let's talk about how to make ether. So again, when you're studying organic chemistry, it's so organized that you can easily follow. I know it's a lot to study, but it's so organized. What I meant by that is, you see a section for naming, you have a section for how to make those functional groups, and then another section that talks about the property of the functional groups, and the fourth one, which is the largest one, is the reaction those functional groups participate in. So when you are studying, you should use that. Make sense? Does it? It's broad, but you know, it's organized. Well, you can have organized mess, right? So, but it's actually it's easy to follow if you do it that way. If you're just opening your textbook and you're switching to any page, you get lost. Start with the naming, and then go to how do you make this functional group, and then what do they react with, and what do they get? Okay, well, it's easy to say, right? Okay, so let's talk about how to make ether. Okay. One way of making ether is through dehydration of alcohols. Dehydration of alcohols. Now you will say that, well, dehydration of alcohols gives you what? Alkene, correct? That's like a conflicting statement there, right? Dehydration of an alcohol gives an alkene. Well, the reason dehydration of an alcohol gives an alkene is because you're dehydrating that alcohol with acid in the presence of water, right? So when that acid, if you look at the mechanism, when that acid protonates your alcohol, correct, the O- that you have left is going to remove, to get back its proton, is going to remove the hydrogen from another carbon to kick out the protonated alcohol, and you get a double bond. So as a side product, what do you get? You get HOH, correct? Making sense? Now, instead of using water, if you have excess of the alcohol, okay, that second molecule of the alcohol is going to be acting as a nucleophile instead of as a base. Okay? And when it acts as a nucleophile, it's going to attack your electrophilic carbon that is bearing the OH functional group and form another O carbon bond, oxygen carbon bond, which gives you the ether. And that is what is shown in the mechanism here. So here you're using two equivalents, these two means two equivalents of the ether in the presence of an acid, okay? In the presence of an acid. So this acid is going to protonate that, and you have this from one, that from the other equivalents. Okay? So let's look at the mechanism in the proper sense of it. Your oxygen here is your Lewis base, correct? Picking up the proton from the acid to get you a protonated alcohol. So this is plus, and you still have a lone pair of electron there. Okay? That makes this carbon here to be very electrophilic. Okay, and you have the second equivalence of the alcohol acting out as, so that's your nucleophilic site. So the oxygen is your nucleophilic site. So with its lone pair of electron, is going to attack that electrophilic carbon, kicking out. And this electron will be pushed onto the oxygen, kicking out the water molecule. Okay? So now you have that water molecule that you kicked out. then you still have a positive charge. I should have inverted that, but that's okay. So this water molecule that you kick out now is going to act as a base. So I'm going to draw it, I'm going to redraw it down here so that it doesn't look messy. So this is going to act as a base, picking up the proton that you have from your protonated ether, and you get a free ether, regenerating the acid that you started with. So that's why you call the acid a catalyst. Okay. So that's how you get that. Okay. So when you use two equivalents, you get your ether. Now, this is an SN2 reaction. Okay, it's by SN2 mechanism because you don't have a carbocation intermediate generated, right? So it's SN2. And one of the criteria for SN2 reaction is one is inversion of stereochemistry, the other is you have to do it at a primary carbon center. Okay, at a primary carbon center. So this method works well only for primary alcohols. Okay? If you use any other thing other than primary alcohols, you will get a competing E1, E2 reaction, elimination reaction, instead of a substitution reaction. So you should go and review that. E1, E2, SN1, SN2. Okay? See how everything is connected? Yeah. Okay. So to circumvent the competing reaction of the E1 and E2 with this SN2 reaction, if you need to make ether with other carbon center other than primary, so let's say you want to make ether with secondary carbon center, tertiary carbon center, you can use a named reaction that is called Williamson ether synthesis. Okay, Williamson ether synthesis. All right. So in Williamson ether synthesis, you generate an alkoxide of your alcohol, and that alkoxide is going to react in an SN2 fashion with an alkyl, primary alkyl halide, or a tosylate, because they are both good living groups. Okay. And to generate your alkoxide, so if you remember under the properties of alcohol, you should go and review that in chapter 17, right? Under the properties of alcohol, we said alcohol can act as an acid. So when you treat them with a base, you generate an alkoxide. So what are we saying? So basically, if you have, let's say you have this alcohol, okay, and you treat it with base, that base can remove this proton. It can deprotonate the alcohol, and you get an alkoxide. Okay? You get an alkoxide. Alright? This alkoxide is what acts as a nucleophile in Williamson ether synthesis. Okay. Now, in Williamson ether synthesis, you always want to make sure that your alkyl halide is a primary alkyl halide. Okay. So if you want to make ether that has one side as secondary or tertiary and the other side as primary, right? Remember, it's two alkyl groups that bonds to the oxygen. So if one side is secondary or tertiary and the other side is primary, you want to make the secondary and tertiary your alcohol, and then the primary side your alkyl halide. Okay? Make sense? All right. So let's see an example here. Before I do the mechanism, let's cross the mechanism out and put it a little bit lower, because something came to me when I was reviewing this that I should break this down for you. Okay. So I know by now a lot of you has gotten used to the fact that when you have 1 and 2, you know that this is saying that you're adding this first and then adding that next. Okay. But another way that the question could be set, which is basically the same thing but throws people off if you're not used to it, is I'm going to break it down like this. Okay, so people might get confused that, okay, is this the same thing as what is up there? Yeah, the only difference is this is showing the intermediate. So when you first treat this with sodium hydride, which is your base, okay, so that's your base. It's a very strong base, stronger than your NaOH, and is usually used when you need a strong base that's easy to handle. There are stronger bases than that, but yeah. So in this case, the intermediate you obtain here will be this alkoxide, stabilized by the sodium, and of course the hydrogen will combine with the other hydrogen from the hydride and forms H2, and it will be given up as a gas. Okay, and then this can now attack your alkyl halide. Ooh, what a drawing! Oh my goodness. And we can have this. Okay. So that is showing those reactions in stepwise order. All right. Now, what's the mechanism? So okay. So this can take that hydrogen. This will go to the oxygen to give you the alkoxide stabilized by the sodium. So hydrogen is given off as gas. Now you have your primary, the iodine. When you're drawing this, I got email from people asking questions about how that's okay. They drew the mechanism and it was showing that it's incorrect. And I looked at it, I responded to it. When you're drawing mechanism, what you're moving is electrons. Okay, so if you want to draw this arrow, you have to pick electron and move that electron to the atom where you want it to go to. Don't pick the negative charge. Okay, you're picking electron. All right, and after that, the electrons in this bond is what is going to be moved onto iodine. Okay, and you will get this, and of course plus sodium iodide, which you basically don't care about. Okay, all right. So let's look at an example here on how to make this. Synthesize tert-butyl methyl ether. So that means you have to first know the structure before you can do the synthesis. If you do not know the structure, that means your answer is going to be incorrect from the beginning. Right? So that's why naming is very important. Okay? Alright, well, I gave you a hint there that the bulky substance should be the alkoxide. Well, let's draw the structure out first. You have a tert-butyl and a methyl. I don't like showing the CH3 when you're doing skeletal structure. You don't have to show it. Okay, so that's our third butyl methyl ether. Okay, this is well, let's call this the bulky group to make it easier. And this is the smaller group. Okay, so when we want to make our ether, that means the bond that we will form will be this bond. Okay, it will be that bond. So if we break that bond, we're going to have this oxygen plus this CH3, right, with a positive charge. Let's put a positive charge there. Okay, but that's not the end. So that means what we're going to start with will be an alcohol from this bulky group plus this is an electrophilic center. So that means we have to make a bond with this carbon that makes it electrophilic. So therefore we'll connect an electronegative atom to that carbon to make it electrophilic, because that electronegative atom will be pulling electrons away from it. Okay? So the starting substrate that we need, the actual starting substrate that we need to synthesize the third butyl methyl ether will be these two reagents. Okay? You are not done yet. It is asking you to propose the best way to do it. What I showed here is a retrosynthesis, is working backward. Okay? Breaking the bond to show what you will start with. Okay? Now you have to write the reaction.
Can you move the page up?
Yeah, I will. Okay, now you have to write the reaction. Okay? So in the reaction, you'll have to treat your alcohol. If you're not asked to show the mechanism, you don't have to show the mechanism. So we're not asked for the mechanism here. We're just going to draw the reagent. So the first reagent we'll use here is a base that will get us our alkoxide that we need. Okay? Okay? And the second reagent that we'll use will be our alkyl halide. You can use bromide, you can use chloride, so you have to pay attention to the wordings of the questions. If the question asks you to write the alkyl halide, then you can write any. If the question is specific, if it says alkyl bromide or alkyl chloride, make sure you're putting chlorine or bromine, because it's going to be different. If you're required to put bromine and you put chlorine, even though it will work, it's not answering the question. Okay, so please pay attention. All right, so over here, this will now react and get us our CH3. Okay, make sense? Yes. Okay. All right, another way to make ether, we'll talk about the other way to make it and we'll stop there. Another way to make ether is through alkoxy mercuration of alkenes. Does this sound familiar? Oxymercuration, right? Oxy, because you used water. If you remember oxymercuration of alkenes to give you alcohol, you use a mercury acetate as the catalyst in the presence of H2O mixed with THF. Remember that? Okay, so that H2O is what made you to get the alcohol. If you switch that H2O to an alcohol, you won't be getting alcohol again, you'll be getting ether. So that's what this chemistry here is talking about. So instead of water, you're using alcohol. So if you go and review the mechanism for the oxymercuration of alkene to get alcohol, you see the same thing. Okay? So here, instead of water, you're using alcohol. That is why that alcohol is adding here. Okay? So the addition follow Markovnikov rule, which means your incoming nucleophile is going to add to the more substituted part of the double bond. Okay? So in this case, this carbon here is the more substituted side. So that means your alkoxy from the alcohol is going to add to that carbon. Alright? Let's see if we can just review the mechanism here. Oh boy, mechanism. Alright, so this is, I'm going to draw this as phenyl. Okay? When you treat this with your mercury acetate, just going to draw the bonds. Okay, let me put it this way. Oh boy. Let me draw it out. Okay. Then the CF3. So that means the mercury is bonding to the oxygen, then carbonyl. Okay. So your electron goes to mercury. This will come back here. Kick out one of the group. So I've used color pen there, but that's okay. So you're going to have a mercuridium bridge. So the mercury is here, and then you'll be left with one of the O2 CF3 because you've kicked one out, and this is going to have a positive charge on. So that's your intermediate. Okay? Because you have this intermediate, which is similar to oxymercuration, because you have this intermediate, this positive charge, even though it's showing on mercury, it's actually kind of delocalized over these two carbons. So it's either it's there or there. Then you have to think about stability of carbocation intermediate. This is like carbocation intermediate. So this positive charge is going to be more stable on this secondary, tertiary carbon center over that. Okay? So when your alcohol comes in, so in this case you say CH3, the lone pair of electrons on the oxygen is going to come in, attack that, this will break, and that's how you get this intermediate that you're given here. Okay? That's how you get the intermediate. Of course, there's one more step. McMurray is trying to save time with pages or stuff like that. So when this adds on, there's still going to be a positive charge on this oxygen because of this hydrogen. Okay? And that will be taken off to get a neutral compound like that. And then the final step is treatment with sodium borohydride to get you to knock out the mercury, and you get your final product. Okay? All right, another example. Okay, so this is your alkoxy, which is the etoxy. And that etoxy is what is adding to this double bond over here. Okay, so that's how the autopsy came from. All right, so we're going to stop there, and I'll see you at 2 and 3. For those of you that came in later, I have graded quizzes. Your graded quizzes are here. You can pick them up. And then the answer keys are online.